lecture will be delayed like 5 minutes. Can we start after 5 minutes with your approval and invited lecture prof's approval?
Yes, please.
Okay. Okay. Thank you, Professor. Thank you. Thank you.
So can I start now?
Professor, you can close the camera if you want. I can inform you just 2 or 3 minutes before we start the session.
Excuse me. So okay. So okay. Please.
Actually, the keynote lecture was going on, Professor. It takes like 5 or 10 minute delay. So we are
Okay, no problem.
informed
Okay.
to start after 5 minutes. Actually, the
Okay.
scheduled time is 10:55 Indian time. We can start around 11 a.m.
Okay. Okay.
Indian time.
Thanks.
Okay, Professor. Thank you. And dear professors, students, and researchers, welcome to the session 3F, Industrial Nanotechnology Products and Commercialization. Professor Minami,
Yes.
Shall we start?
Yeah, please start.
Professor Kimura?
Yeah.
Shall we start, Professor, the session?
Yeah.
Okay. So welcome to the session. The session chair, Professor Tsuyoshi Minami from Shizuoka University, Japan. His research interest includes supramolecular analytical chemistry, self-assembled materials, gold nanoparticles, and organic transistors for sensing applications. He received so many awards. Some of it are Japanese Photochemistry Association Award for Young Scientist 2020, SG Japan Award for Excellence 2020, Encouragement of Research in Polymer Science, Young Researcher Award of the Electrochemical Society of Japan, Young Innovator Award on Chemistry on Micro Nanosystems, the Chemical Society of Japan Award for Young Scientists, etc. He got until now he got a H-index of 27 with citations around 1633. With this introduction, I kindly request Professor Minami to chair this session. Thank you.
Okay, thank you very much for your kind introduction. Actually, so I'm from the University. Sorry, that is just but that's a mistake. Anyway, so I'm very happy to have the chair in this session. So I'd like to introduce the two invited lecturers and the two contributors' presentation. So first, presentation from the Professor Kimura. And also invited lectures, yes, Professor Kimura. So he has worked for Organization for Innovation and Social Collaboration years, and now he is challenging to long-term cultivation of human resources. His mission is to utilize technology developed by the university in industrial fields to contribute to the society. So his research interests manufacturing technology, including mechanical, electronical, electrical, electronic, chemical engineering, and also electronic devices and equipment. So Professor Kimura, please.
Thank you very much. So can I share? Can you see my slide?
Yes.
Okay. Thank you very much. First of all, thank you, Chairman, for good introduction. And I'd like to express my appreciation for organizing committee for giving me this opportunity. This is my self-introduction. I'm a trustee and vice president of Shizuoka University, and I'm sorry my presentation today is not a professional scientific presentation, rather introduction of research potential of Shizuoka University. And my term of VPR will be expired soon, so maybe this is the last opportunity to talk about Shizuoka University as a VPR, and maybe you know TED, and I had the chance to talk about education on TED, local TED. It's called TEDx Hamamatsu. You can find my speech searching TEDx Hamamatsu and Kimura. Okay, this is my research field. Actually, now I'm acting as a vice president, but maybe 10 years ago, it is a long time ago. Actually, I was a researcher on, originally I'm research on the crystal growth of semiconductor crystals. And then I extended my field to semiconductor devices, especially power devices like static induction transistor families and the pulsed power applications. Then I moved to the Industry University Corporation as a manager for technology transfers. After I became BPR, I'm kind of salesperson for Shizuoka University. Maybe it's a good idea to explain from the population in Japan. First of all, I'd like to kick off my presentation from the population trends in Japan. This is a population triangle in 1980. This shows a beautiful structure of normal population pyramid, which means Japanese population structure is healthy. But the situation is changing, like 2015 and 2030. Actually, 2030 data is just prediction, and it will show the inverse type of pyramid. This is a very dangerous situation for Japanese society and even for universities in the near future. The battle of student acquisition between university will begin soon. And figure shows the distribution of Japanese national universities. In 2000, we had 99 national universities, but the decreased now to 86. And in each prefecture, we have at least one national universities. In Shizuoka University, we have two universities in this Shizuoka prefecture, and one is Shizuoka University, and the other is Hamamatsu University School of Medicine. In 2004, we had a drastic change for national universities in Japan. Before that, all Japanese national university belongs to federal government. All Japanese national universities became incorporated to National University Corporation in aiming at more autonomous operation from the government, financial management, human resource management, and midterm goals and planning, and evaluation by MEXT. MEXT means Ministry of Education. Okay, I go to the explanation of the Shizuoka prefectures. Actually, Shizuoka prefecture is located in the center of Japan and exists between Tokyo and Osaka. And as you can see, in Shizuoka prefecture, we have Mount Fuji, and Shizuoka University has two campuses. One is in Shizuoka City. It's a capital city of Shizuoka prefecture, and the other is in Hamamatsu City. Actually, the Shizuoka prefecture has lots of industries and also historical heritages and variety of foods and hot spring in Izu Peninsula. In Shizuoka prefecture, we have lots of industries. It's startup companies and photonics and electronics and transportation and music instrument. And we also have lots of foods and pharmaceutical companies. And I mentioned before, but we had hot spring. It's called onsen in Japanese in Izu Peninsula. And also Shizuoka prefecture has lots of number ones. Of course, the mountain, the Mount Fuji is number one, and tea and tuna cans. And maybe you know the plastic model. This is a very famous Gundam and the music instrument and motorcycles. And now maybe this data is very old. And before we have lots of soccer players from Shizuoka prefecture. And this is introduction of Hamamatsu City. And Hamamatsu is just a local city, but it produced a lot of innovators and global companies like Yamaha, Kawai, and Toyota. Toyota is originally from Hamamatsu, and Suzuki and Honda, and the Hamamatsu Photonics. But we also had the problems like local cities like Shizuoka and Hamamatsu are facing the crisis like population reduction. In Japan, except Tokyo, the small cities are losing population because low birth rate, and also the people are absorbed to Tokyo. This is also the big problem for the Japanese universities. Okay, back to the Shizuoka University. And we had two campuses in Shizuoka campus and Hamamatsu campus. And this is the brief overview of Shizuoka University. We have 6 faculties: humanities, education, informatics, science, engineering, and agriculture. And Hamamatsu campus, we have informatics and engineering. And we also have the graduate school, 5 graduate schools and 2 research institutes. I explained later this. And we have students, we include all undergraduate, masters, doctors, about 10,000 students in Shizuoka universities. Okay, we have the Office of Research Strategy in Shizuoka University. As we are working on the research analysis and support as a basis of knowledge and the strategy for priority research areas and research support to increase strengths and characteristics. And we promote the 3 areas of research that optical application and imaging science and environmental and energy science and green biosciences. And I explained we have 2 research institutes. One is Research Institute of Electronics, and the other is Research Institute of Green Bioscience and Technologies. Okay, this is figure shows first, but maybe you think this is Mount Fuji, but this figure shows the people. But those are research fellows and young leading researchers of Shizuoka University. And with those research fellows, Shizuoka University, and maybe this guy is, he's going to present next presentation after my talk, and he's Professor Mimura. And those researchers, research fellows, but they just got a little bit bonus and also just business card. They are their incentive selected as research fellows. And those are young leading researchers in Shizuoka universities. But young researchers got a research budget from university as an incentive. Okay, this is the Research Institute of Green Science and Technology, which consists 3 divisions. One is Green Energy Research Division, and Green Chemistry Research Division, and Green Bio Research Divisions. They have very excellent researchers, and they always successfully got research monies and performed a very good result of researchers. And this is the other research institute. It's called Research Institute of Electronics, established in 1965. The history of this institute is initiated by the great inventor, Professor Kenjiro Takayanagi. And Professor Kenjiro Takayanagi project Japanese character E, Japanese alphabet E, on the brown tube in 1926. And actually, this is the first invention of electronic television system. After the innovation of the Professor Takayanagi, Shizuoka University focused on the imaging technologies at Research Institute of Electronics and got a lot of research fund supported by Japanese government like this. And this is a innovative photonics evaluation research center called IPARC for cutting edge photonics research for universities and companies, is established on Hamamatsu campus in 2015. Actually, this is a research center and it acts as an incubator for new startup companies from universities and act as a center for the open innovation. This figure shows we had a photonics declaration in Hamamatsu for Shizuoka University, Hamamatsu University School of Medicine, and also Hamamatsu Photonics. We try to make the research core in Hamamatsu City, and also we'd like to develop a new industry from Hamamatsu City. And now iPerg, it works as an open innovation center for industry. We have a lot of collaborative research with the industries. We have many research seats like X-ray CT, imaging devices, color fidelity, remote reduction, news, and terahertz devices. Okay, this figure shows a R&D collaboration situation for Shizuoka University. As you can see, we have a number of research collaboration is increasing, and this is very good. And also we have the collaborative research labs in Shizuoka University, and also we have the project research institute, and we review the cost of indirect cost. Now we raise the indirect cost to 30%. It's a little bit controversial, but it helps the management of the university. And now I go to the startup companies. Shizuoka University, we have 36 startup companies from Shizuoka University. This number is very big as a local university, and it means you can find our research activities and also our entrepreneurship for students. Okay, those are the figure. It shows the licenses or patent to startup companies and also the small companies like SMEs. As you can see, we have lots of licenses to those small companies. This means we utilize our patent, and also we support those small companies, small businesses. Okay, this is one example of our startup company. It's called Brookman Technology, and they developed 8K high definition imaging devices. Those are used in the NHK. It's a broadcasting company in Japan. They are 8K image sensor using the technologies invented by Shizuoka University. The imaging technology of Shizuoka University has a very high achievement in academia as well. We now have the #1 position of papers in ISSCC like this. As I mentioned before, the sensor is utilized by the NHK and used for the broadcasting for 2020 Olympic Games in Tokyo. We are so proud because we are the inventor of television, and now we also developed 8K sensor after 100 years. Okay, those are examples of application of 8K cameras. It will be used for many areas like broadcasting, medical. Now we have the 8K camera endoscope and video conferencing, and also security. And this is the other startup company. They are developing X-ray CT. Maybe X-ray CT is the theme for the Professor Mimura after my presentation. And this company is developing X-ray CT and also high energy detectors. The name of this company is called Unseen. It means this company can make unseen to seen, and unseen means also the meaning in Japanese is safety. So it has two meanings. Okay, actually, this is a real production of Shizuoka University, Japanese sake, and Shizudai Sodachi. And it's very interesting because this is really made by Shizuoka University. Because the brewmaster of this sake is our alumni member, and the rice for this sake is cultivated on the Shizuoka University farm of the Faculty of Agriculture. So this is really 100% Shizuoka University development, and this is very tasty. Okay, then maybe this is the last present seed. This is a local innovation ecosystem, which is Shizuoka University tries to establish with other universities and also municipalities and industries supported by Ministry of Education. Now we have the commercialization project, and those are stage of the commercialization. Our target is a new endoscope. You try to develop an invasive 3D endoscope, and also new TOF sensors. TOF means time of flight sensors, and also color reproduction technologies. Those are very close to the market. And we also had very close next generation core technologies. And it's a new oximeters. Actually, our oximeter is not old one. It's we don't need artery. If we have the blood, we can measure the saturation of the oxygen, and we have the X-ray source. Maybe this is introduced by the Professor Mimura, and we have new ion sensors, manufacturing technologies, and antibio dressing, and drug evaluation by telehealth. And those new technologies we now have researches by Shizuoka University professors. Okay, that's all for today, my presentation. Thank you very much. And if the students interested in my talk, please join Shizuoka University. Shizuoka University welcome students from India. Thank you very much.
Thank you very much for introducing Shizuoka University. I enjoyed very much. So the audience, any questions or comments if you have, please? Okay, if not, okay, I have a couple of questions. So I was surprised, so many venture company in the Shizuoka University there. Do you have any special support for the professors or the inventors?
Actually, we have some programs because we try to help their management, and also we connect some banks to support their management, and also we have some programs for students for entrepreneurship. Those maybe increase our number of the startup companies, maybe.
So I see this. That means the Shizuoka University can support, for example, some like the staff and also the money, and so sounds great. So I was surprised. Yeah. Okay. Any other questions? Yeah. Or comments?
No other questions.
Yeah, please.
No comments in the comment box also. You can
comments?
The next topic.
Yeah.
No comments, Professor.
No comments. Okay.
Okay. Thank you.
Okay. Thank you very much. Nice talk.
Thank you very much. Yeah. Thank you.
Thank you, Professor.
Thanks.
Yeah. Okay. Next is okay. I would like to move on the next talk. So next is Professor Mimura from Shizuoka University. Yes. Could you move on? Yes. So Professor Mimura is a professor with the Research Institute of Electronics, Shizuoka University, and has been a director of the Research Institute of Electronics since 2006. He is an honorary professor of St. Petersburg State Institute of Technology and an adjunct professor of the University in Indonesia. He has published more than 210 papers. He is a leading researcher with Shizuoka University. He has been engaged in vacuum now electronics and imaging devices. So Professor Miura is a member of the Japan Society of Applied Physics, the Institute of Electronic Information and Communication Engineering, the Institute of Imaging Information and Television Engineering, and the Vacuum Society, excuse me, could you go back? Yes, and the Vacuum Society of Japan, the Society for Information Display and the IEEE. So, Professor Miura, please start.
Thank you very much, Mark. So, do you hear me?
Yes, I can see your voice.
Yeah. And so I'll share my, okay. Okay. Okay, do you see the slide?
Yes, I can see.
Yeah. Okay. So I'm Hidenori Mimura from Research Institute of Electronics, Shizuoka University. My title is X-ray generation using the pyroelectric crystal excited by a laser light. Okay. Pointers on. And then, okay, these are the contents of my talk today. So first, I'd like to talk about the motivation and the purpose of this work. And in this work, we develop novel X-ray source using the pyroelectric crystal excited by laser light. So at first, I'd like to talk about the motivation and purpose of this work. And then I'll talk about the experimental results of the novel X-ray source using the pyroelectric crystal excited with the UV laser. And then I will speculate the operation mechanism. The last is conclusion. So I'd like to talk about the motivation of this work. So X-ray sources are widely used X-ray apparatus and CTs. This slide shows a schematic of a conventional X-ray tube. So in the conventional X-ray tube, tungsten filaments is heated and the electrons are accelerated by the high voltage source. So typically a 30 kilovolt to the 200 kilovolt. The accelerated electrons bombard the metal target and then X-ray is irradiated from the target. In the conventional X-ray tube, so high vacuum and high voltage source and high voltage cable are necessary. The X-ray source which does not need the high vacuum, high voltage source and high voltage cable. So this is commercialized by the Amtech increment. So this is a Curex. This is a very compact X-ray source. This figure shows the inside of the Curex. In the Curex, the main elements are pyroelectric crystal and also the Peltier devices. This slide shows the X-ray generation mechanism in Curex. In a pyroelectric crystal, spontaneous polarization is generated like this. This spontaneous polarization is cancelled out by the charges on the surface at room temperature. So this spontaneous polarization is cancelled out. The temperature is increased by heating with the aperture devices. The spontaneous polarization so decrease, and the surface potential so becomes negative. The electrons are emitted from the top of the surface of the crystal and accelerated towards the metal target, and the X-ray is generated. This is the output X-ray spectrum obtained the Cool-X. So X-ray up to 35 kilovolt is obtained without any high voltage source. The advantage of the Cool-X is the compact. No need for high voltage source. No need for high vacuum. No need for high voltage cable. However, disadvantage point is the slow response due to the heat capacity of the Peltier devices. So I'd like to talk about the purpose of this work. So I'd like to develop a compact CT with a multi-X-ray sources and multi-X-ray detectors. And this is a concept. So these are the multi-X-ray sources, and these are the multi-X-ray detectors. So I'd like to develop the very compact CT system. To switch each X-ray source with an optical switch, I'd like to switch each X-ray source with an optical switch. So because the optical switch is expected to achieve a fast response. To generate X-ray and switch optically each X-ray source, we have used the pulse laser instead of the Peltier device. This slide shows the experimental setup of the novel X-ray source. We use a copper target and cylindrical lithium niobate pyroelectric crystal. The size of the lithium niobate is 4 millimeter length and a diameter of the 10 millimeter wide. The pressure inside the vacuum chamber was 0.3 Pascal. So we detected X-ray from an X-ray detector and measure the temperature of the lithium niobate crystal with a thermocouple. So we use a pulse UV laser to excite the lithium niobate crystal. So we use two pulse UV lasers. One is the fourth harmonic of the pulse neo-GIAG laser. The wavelength was 266 nanometer. The power was 400 milliwatt, and the pulse width was 10 nanoseconds. The repetition rate was 10 Hz. So photon energy of the wavelength of 266 is larger than the bandgap energy of the lithium niobate. And the second one is the third harmonic of a pulsed neo-GIAG laser. The wavelength was 355 nanometer. The power was 400 milliwatt. The pulse width was 6 nanoseconds. The repetition rate was 10 Hz. So in this case, the photon energy is smaller than the bandgap energy of the lithium niobate crystal. So this slide shows a temporal response of the X-ray generation excited by a 266 nanometer UV light. So this line indicated the dose rate, and this line indicates the total dose. when the laser is irradiated, X-ray generates and dose rate gradually increases. The maximum dose rate of about 3 milligray per minute was obtained, and the total dose of 2 milligray was obtained for 130 seconds. The X-ray generation includes at the first and then gradually decreased, even though the lithium niobate crystal was still excited by the pulse UV laser. So this means the electron supply on the surface of the lithium niobate crystal is slower than the electron emission from the lithium niobate surface. So X-ray emission suddenly stopped due to the discharge. This slide shows the X-ray spectrum, generated by using the kappa target and a lithium niobate crystal excited by the 266 nanometer UV light. The energy spectrum shows K alpha, kappa, and K beta, kappa characteristics X-ray peaks attributed to the kappa target, and the bremsstrahlung X-rays. Bremsstrahlung X-rays was observed in the higher energies up to 30 kilo electron volt. So this indicates the electron emitted from the lithium niobate crystal. Electrons bombard the kappa target during the laser irradiation, and the X-ray is generated from the kappa target. So this slide shows the increased temperature of the lithium niobate crystal during the 266 nanometer UV laser irradiation. For UV laser irradiation of about 90 minutes, 540 seconds, the increased temperature was very small and only about 4 Kelvin. To generate X-rays, heating the lithium niobate is usually necessary. However, in this case, no increased temperature of the lithium niobate crystal was observed. So in this system, we don't need any rise in temperature. When we used the 355 nanometer UV laser, in this case, so photon energy is smaller than the band gap energy of the lithium niobate. So in this case, the X-ray was not generated. So when we irradiated 355 nanometer UV light directly to the lithium niobate crystal through the quartz glass, no electrons are emitted and no X-ray was generated. Therefore, we inserted the kappa plate between the lithium niobate crystal and quartz glass. So in this case, 355 nanometer UV light heats the kappa plate, and then kappa plates heat the lithium niobate crystal. In this case, X-ray was generated. Electrons are emitted from the surface of the lithium niobate, and the X-ray is generated, and it is due to the thermal effect. This slide shows the temporal response of the X-ray generation excited by the 355 nanometer UV laser. So in this case, the maximum dose rate of about 1 milligray was obtained, and the total gray is 0.3 milligray was obtained for the 200 seconds. The dose rate is 1/3 lower than that of the direct excitation of the lithium niobate crystal using a 266 nanometer laser light. From these results, we speculated the electron emission mechanism. When we excited the lithium niobate crystal with a 266 nanometer UV light, electron emission is not due to the thermal effect. The absorbed UV light so generates electron hole pairs in the lithium niobate crystal, and this electron hole pairs so decrease the polarization in the lithium niobate crystal, but the detailed mechanism is not clear. On the other hand, in the case that we excited the lithium niobate with the copper plate using the 355 nanometer UV light, in this case, electron emission and the generation of X-ray is a thermal effect. At present, amount of X-ray generation is low, so we added the isopropyl alcohol inside the vacuum chamber during the laser on. So this figure shows a temporal response of the X-ray counts. So without isopropyl alcohol, the peak count was about 40 CPS. On the other hand, when isopropyl alcohol was present, the peak counts increased to about 4,500 CPS. So moreover, the duration of the X-ray generation increased so significantly. Okay, let me summarize my talk. So we have succeeded in generating the X-ray by exciting the lithium niobate crystal with a 266 nanometer pulse UV laser. So the X-ray source is compact and does not require any external voltage. And the rise in the, and also we don't need the rise in temperature of the lithium niobate crystal during UV laser irradiation. So we'd like to apply this X-ray source to the compact CT with the multi X-ray sources and multi X-ray detectors in the future. So thank you very much for your kind attention.
Okay, thank you very much for nice talk. Yeah, I appreciate very much. So the audience, and if you have any question or comment, please. Do you have any comment or question? Okay, I have a short question. Actually, excuse me, some guy, do you have any question?
Yes, Professor. I have one small question.
Please.
How using laser we excited the lithium niobate. So the thermal stability is important or not important in the case of lithium niobate?
Thermal stability, if the temperatures are below the Curie temperature, in this case, so thermal is not so important.
Okay.
The power of the laser is also important.
Thank you.
Okay, any other questions or comments, please? Okay, if nobody have the questions, okay, I have a small question. So actually, I'm not familiar with this field, but I noticed that you dramatically decrease the voltage. That is quite amazing. So what is the next, like the technical problem or like the scientific problem to develop the further better like the machine or instruments?
So the technical problem is it's the power of amount of the X-ray. Dose rate is low for the applying this X-ray tube to the industrial CT or the X-ray tube. And another big problem is I don't know the mechanism, operation mechanism. So I don't understand the mechanism. So the okay, so I don't know the how the photon, how photon, so the decrease the okay spontaneous polarization. I don't understand so what's the mechanism. That mechanism. So I need the basic research. We need the basic research more and more.
I see. Okay. Sorry, I also could not understand what is the role of the IPAs, isopropyl alcohol? The last
Okay.
slide.
Yes, and it's in this case, so the electrons so attach the surface of the lithium niobate crystal and emitted. When we use the high vacuum, so amount of the electrons is small. So the supply of the electron is disappear or we cannot supply the electron. So we enhance the amount of the electrons inside the vacuum chamber. Okay, so the isopropyl alcohol acts such supply of the electron on the surface of the lithium niobate.
I see. Now I understand. Okay, thanks.
Okay.
Okay.
Thank you very much.
Okay, if you have no any other questions, I'd like to close this talk. So thank you very much for a nice talk.
Thank you very much.
Okay, next I'd like to move on the contributors. So
Next contributor lecture professor.
これかな。はい。
ありがとうございます。Okay, so let's move on the contributors talk. The first is so roughly 10 minutes talk. So the first guy is Dr. Shamal Kumar Das. The title is A Low-Cost Rechargeable Battery with Aluminum and Graphite. So Dr. Shamal Kumar Das, please.
Okay, let me share the screen. Dr. Das, your voice is not audible.
Is it audible?
Yeah, now it's okay.
Audible, right? Screen
Yeah.
can be seen, right?
Yeah.
Presentation?
Your voice is. Yeah, now it's okay. Please hold your mic near to your mouth. Now it's okay. Yeah, your PPT is visible.
Okay, fine. Can you hear me?
Yeah, okay.
Okay, fine. Okay. So first of all, I'd like to thank you. Thanks the organizer for considering me as one of the speaker in this conference. And today I'm going to talk about a rechargeable battery based on aluminum and graphite. So it is needless to mention about the importance of lithium-ion battery in our society. It has been extensively used almost all electronic devices as well as in our electric vehicles. But however, with time, there is a growing concern about the sustainability of lithium-ion batteries. Why is that so? Because the lithium minerals, whatever that is in the universe, we can extract only for 60 years. And this is an ideal calculation. It may be even lower than that. And another disadvantage is that lithium-ion batteries cannot be assembled in ambient atmosphere. We always need special conditions for the fabrication of lithium-ion batteries. So in this context, I'd like to pose a question that can we make a rechargeable battery at our home with low cost resources and with minimum safety precautions? And the answer is yes. And the answer is yes. And this video footage and this photograph is a testimony of a rechargeable battery. Here is our aluminum graphite battery. As you can see here, this battery could power an electric motor, as well as it can help in powering few LED lights. So as I mentioned here, we used some kind of low cost resources. What are those low cost resources? Okay, so these are basically 4 ingredients. Number 1, water. Number 2, aluminum. Number 3, graphite. And number 4, aluminum chloride. Okay, now this kind of aluminum foil is very easily available in any kind of grocery shops. And graphite is an extremely cheap material. Okay, and aluminum chloride is also very cost-effective material. So these are the 4 ingredients we need to have our aluminum graphite battery. Okay, so in this photograph shows our aluminum graphite cell. So here we have one electrode is graphite, another electrode is aluminum, and these 2 electrolytes are dipped in aluminum chloride, water-based electrolyte, aqueous electrolyte. And now, whenever we combine graphite and aluminum, we see a potential difference between them. And whenever there is a potential difference, there is a flow of current. Okay, that is the basic fundamentals of a battery. Now, if it is a battery, does it work so easily? The answer is no. Okay, why I'm saying no? Because when you perform the electrochemical investigation to see how good it is, we have seen that during discharge process of the battery, that means when you are drawing current from the battery, we see a specific capacity of only 8 milliampere hour per gram. However, for comparison, I have noted down here, lithium-ion battery, this number should be more than 140 milliampere per gram. So in comparison to lithium-ion battery, obviously our aluminum graphite system is very inferior in terms of performance. So we pose 2 questions again: why it is showing poor performance and how to improve it. Let us first discuss the why. Whatever graphite we use in our cell, that is very compact and bulky in nature. We use 0.5 mm thick graphite. Now fundamentally, if we look at it, if we consider this is the piece of graphite, that graphite is having certain graphene layers, and this aluminum ions from the electrolyte comes to the diffuses inside this graphene layers, and the electrons from the external circuit travels to the graphene. This is a coupled process. So what happens is that if we use bulk graphite, then there are a large number of graphene sheets, and all the graphene sheets cannot be used by aluminum ions. There are few unused graphene layers. So that is why we see less storage of aluminum ions. On the other hand, if we use few layer graphite, then all the there are only few, let us say 4 or 5 number of layers, then all the aluminum ions can access all the graphene layers available in that graphite. So more storage of aluminum ions. So we realize that if we use few layer of graphite, then we may be able to improve the performance. And it is really so. When we perform the experiment with few layer graphite, we see a dramatic difference compared to our initial experiment. Initially, we got only 8 milliampere per gram. Now we got 200 milliampere hour per gram. Not only that, we could achieve 1.8 voltage of battery. Okay, this is a very remarkable result so far aluminum graphite is concerned. Now, how do we get that few layer of graphite in a very simple and scalable way? Okay, so it is very simple. So what we did is that we took our cell and apply a DC potential of 4 volt for 5 minutes. When we did that one, you can see the structural change of the graphite. This is the pristine graphite before the application of the 4 volt, and this is the graphite after application of 4 volt. Here, as you can see here, it is a foam-like structure, and we can see that there is 250% of expansion of this graphite foam compared to this graphite. And microscopically, when we looked at it, we have observed that this graphite foam is very porous, and it is filled with some kind of flakes. And with transmission electron microscopy, we proved that these are really nano flakes, and the thickness of one flake is of the order of 8 to 10 nanometer. And with this graphite foam, when we performed the experiment, we could achieve 1.8 volt, and we could achieve very high storage capacities. Now, one obvious question is asked is that what is the evidence that I'm claiming that aluminum ions are going inside this graphene layers? It is sitting inside the graphene layers. Okay, so for that, what we did is that we took the electrode after running the battery for several number of times, and we performed the XPS. This is the electrode of that battery, and we used with XPS techniques to find out whether aluminum is there or not, and we will see the signal of aluminum. It means that aluminum is there, but this aluminum is inside this structure or it is just on the surface, we do not know. To verify that, we use a simple technique. what we did is that we burned this electrode at 800 degrees Celsius under air atmosphere. And when we did it, what you see is that, this black product turns into white product. And when we performed the X-ray of this, X-ray diffraction of this white product, we found that this white product is basically aluminum oxide. So this black product turned into aluminum oxide. That means in this graphite, the aluminum ions are there, and when you burn it, the aluminum turns into aluminum oxide and the carbon just goes away. So this is how we prove that the aluminum ions are really inside this structure. So one of the issues that we faced during this work is that when we run the battery for several number of cycles for several hours of duration, we see that there is a severe corrosion of aluminum electrode. On the other hand, the graphite electrode, we see there is no kind of damage. So we proposed a mechanical refueling model to improve the long-term stability. So let us say this is your aluminum graphite cell. We have one piece of graphite, one piece of aluminum. With time, what is happening? That there's a corrosion of aluminum foil. So what we can do, this corroded aluminum foil we can replace with a fresh piece of aluminum. Okay, so that is how we could extend the cycle number. And as you can see in this plot here, we have 3 different cells, but we use the same graphite foil, and we use 3 different aluminum electrodes, and we could run the cells for larger and larger number of cycles. So we realized that, expansion of the graphite foil, this is your pristine graphite. If we expand it, then we can improve the capacity. Now, can we expand it more? We could increase up to 250%. Can we increase it more? Yes. Now we have found the technique. That manuscript is submitted under review. Technique by which we could expand the graphite foil up to 440%. As you can see here, or in this figure, this is very, very thick graphite foam. And when we use this graphite foam, now what we see is that this is the initial experiment. We could achieve a number of 35 million per hour per gram. When we use this highly thick graphite foam, we could dramatically improve the number. There is a 3-fold increase in the capacity. Not only that, we could get a very stable discharge plateau, or say cell voltage on a battery. So in conclusion, I'd like to say that it is possible to have a low-cost battery with just aluminum and just graphite, and we can assemble it at our home without any safety problem. And since long-term stability is a big problem in our case, so we propose a mechanically refueling model to achieve large number of cycles or extend the durability of the battery. And it is possible because the aluminum is very, very damn cheap material, and we can use it. We can buy n number of aluminum foils from the grocery shop at a lower cost. Okay. With this, I'd like to thank you very much.
Okay, thank you very much for nice talk. Now I'm open for the discussion. If you have any question, please send me the chat. One chat is here. Okay, one question is that, so what is the rate of the current used for the cycling studies? So what is the
current?
So what is the rate of the current used for the cycling studies?
So in this study, we use 1 ampere per gram. Okay, so that is a bit very high current. Okay, we use lower current also, but when you use lower current, since we are working with water-based electrolyte, there are other problems. Okay, since we are using lower current, means we are giving an electric field for a longer period of time, and water may dissociate into either hydrogen or oxygen if we keep it for a longer period of time. So that's why there are technical disadvantages that this kind of cells may not be used for low current rates. Okay, we'll have to go for high current rates only. Okay.
Okay. The other question also here. So, sir, I have a doubt. Like, is there any reason for increase in capacitance value upon the cycling?
Is there any?
So I have a doubt. Like, is there any reason for increase in capacitance value upon cycling?
So increase in capacitance values is very important because that's what will define your energy density. Okay. Now, with time, what we have seen that if we use the battery for longer period of time, we see that there is an increase in the capacity. It is because we are using graphite, and graphite is basically a material which is stacked with graphene layers. Now, initially, it is very difficult for aluminum ions or any kind of ions to intercalate in these layers. But once it intercalates, the expansion between the graphene layers increases. When it increases, then ions can very easily move inside this structure. So that is why with time, you will see, not continuous increase, but after say few cycles, 10 cycles or maybe 15 cycles, you see there is a increase in capacity and later on it stabilizes. Okay, so that is one reason. The reason, to be very precise, is that with time, the expansion of the graphene layer increases, and that helps in accommodation of more number of aluminum ions inside the structure. I hope I could clear.
Okay, also other question is how is a graphite form layer formed which increases storage of the aluminum atoms within graphite layers? How is a graphite form layers formed which increases storage of the aluminum atoms within graphite layers?
Okay. As I already mentioned here, okay. So what is happening here is that the aluminum ion will have to go inside these graphite layers. Okay. Now it is a very bulk material. It's very difficult for the graphene layers to expand. So that is why not all the aluminum ions can go inside these graphene layers. So as I shown in this schematic, there are few layers of graphene which is unused. Unused means what? You are not contributing to the capacity. But if you use only few layers of graphene, let us say 5 layers or 10 layers, then it can very easily expand it. We can very easily expand it, okay, because of ion intercalation. And because of that, more and more number of aluminum ions can go inside this structure. So that is why we get more capacity when we use few layers of graphene or graphitic foam kind of structure. Okay.
Any other questions? So if not, so almost time is up. Okay. Okay. Thank you very much for nice talk again. Okay, let's move on the last topic. So last topic is, could you please share the screen? Yes, next talk is, sorry, I'm Japanese, a bit hard to pronounce full name, Krishna. His talk title. Okay, Krishna Prasad. Okay, his talk title is the zirconium oxide at paradigm core shell nanocomposite on graphene for improved electrochemical detection of methyl parathion. Okay, please start.
Hello, sir. Good evening. Konnichiwa. Am I audible?
Konnichiwa. Can you share your screen?
Yeah, you are audible.
Yes, sir.
I can see your screen. Yeah, please start.
Yes, sir. So at the outset, respected chair, professors, and other participants, a very good afternoon to one and all. And I am Dr. Krishna Prasad, and I would like to thank the organizers of the ICONN-2021 for giving me an opportunity to share my work here. So the current work is titled as zirconium oxide at palladium core shell nanocomposites on graphene for improved electrochemical detection of methyl parathion. So it is important for us to note that there has been a tremendous explosion in population in the world in the last 2 centuries. And this particular population explosion has led to a rise in the demand for food, which has in turn led to an upsurge in the use of pesticides so that we could produce food to meet the rise in demand. It is estimated that the use of pesticides roughly contributes to 1/3 of world's agricultural produce and is one of the main contributing factors in the rise of agricultural production in India. In the last 5 years, the use of pesticides in India alone has risen from 56,000 tons to 61,000 tons. And the use of excessive pesticides over the last few decades, I would say, has resulted in pollution of both ground and surface waters and making animals and humans unintentional targets. Now to discuss how we have become unintentional targets. So if you take organophosphorus pesticides, which is one of the main class of pesticides which is used worldwide, these particular pesticides, when accumulated in the body, lead to irreversible inhibition of acetylcholine esterase, which in turn leads to an increased level of acetylcholine, which is a neurotransmitter in the muscle fibers and also near the neuron centers. And this would lead to different conditions like muscular paralysis, bradycardia, hyper and hypotensions, convulsions, asphyxiation, and it could be fatal for everyone. However, thanks to the development in science, there are different detection methods and protocols for these pesticides, and majority of them being mass spectrometry coupled chromatographic methods and spectrophotometric methods. But the main disadvantage of these methods is the use of costly reagents and extensive sample preparation, and mainly non-mobility. That is, these equipment need to be present in a very controlled environment and cannot be taken into the field. On the other hand, there are electrochemical detection techniques which have the main important function of mobility. For example, we all know how important glucometers have become in our daily usage in the market. And that too, it is thanks to the electrochemical detection methods. So when we come to electrochemical detection methods, we can use simple reagents and we do not have any extensive sample preparations needed, and they can be mobile. However, one of the main problems for electrochemical methods is electrode poisoning, which happens because the different ions and radicals which are produced during the electrochemical reactions in the electrolyte lead to blockage of the active sites of the electrode materials. And the major poisoning agents of these are the commonly present nitrogen oxygen moieties, which become free radicals and attack the electrodes. But we also have an advantage in the sense that this nitrogen and oxygen species are majorly attracted and interact heavily with noble metals. So here we have come up with a strategy wherein if we are using noble metals as sacrificial materials to develop poison resistance, they could in turn enhance the electrochemical activity of the sensors. And bimetallic core shell based materials have garnered significant interest, as it has been understood that the introduction of a secondary metal greatly enhances the electrocatalytic activity and sensing abilities of the primary material. And this is because the absorbed intermediates leading to intrastructural induced promotional effects. So the presence of the second bimetallic metal leads to in structure induced promotional effects, leading to the enhancement of the sensing abilities. Already different moieties like cadmium sulfide on zinc sulfide and other moieties have been tested. These different core shell nanoparticles have been tested for various catalytic and sensing applications. However, suitable supports for these synthesis of nanoparticles is also a key strategy in developing a very good sensor material. And among the different carbon supports, graphene or reduced graphene oxide is a choice of support for many because of its ease of synthesis and enhanced electrochemical properties. So coming to the experimental part, what we have done is that we have synthesized graphite oxide from graphite using modified Hummer's procedure. And this graphite oxide was used in a microwave assisted reduction procedure using hydrazine to synthesize the zirconia on palladium nanoparticles. And This particular composite has been characterized, and its electrochemical properties towards the detection of methyl parathion have been studied. And these studies have been carried out in a 3-electrode system, wherein the working electrode is a glassy carbon electrode, the counter electrode is a platinum wire, and the reference electrode is a silver-silver chloride electrode. And the electrolyte used was a 15 millimolar phosphate buffer saline solution at a pH of 7.2. And the working electrode was fabricated by polishing the GCE and later drop casting 10 microliters of the electrode material, which was dispersed in milli-Q water at 1 milligram per ml concentration. And after drop casting, the electrodes were dried under vacuum at 70 degrees Celsius and were used for further studies. So coming to the characterization, we first recorded an scanning electron micrographs of these materials, and we have found that the synthesis of RGO was successful. And subsequently, we also found that there's an even distribution of the nanoparticles on the graphene. The electron dispersive X-ray spectroscopy was performed to know the percentage loading, and it was found to have very good carbon to oxygen. The graphene was found to have very good carbon to oxygen ratio, and also the nanoparticles were distributed evenly. We in fact wanted to check the core shell morphology of these particles, and hence we did a high resolution transmission electron micrography, and we have found that the particles have core shell nature, and it has been confirmed from the lattice planes that the core is palladium and the shell is of zirconium oxide. And we have also recorded the Raman spectroscopy to understand whether the defect nature of the reduced graphene oxides which has been synthesized, and we have found that from the graphite oxide to reduced graphite oxide, that amount of defects have increased greatly, and this in turn would help us in better anchoring the nanoparticles on the surface of the graphite. And that was the case even in the case of PDZR RGO, which is the composite loaded graphene. And coming to the electrochemical studies, we wanted to the initial response of the composite to the methyl parathion was studied using cyclic voltammetry, and the drop casted electrode was used for recording, and we have found that recording the cyclic voltammograms, and we have found that the initially there is a reduction reaction which occurs at minus 0.73 volts, and this was compared with the response previously shown by without any only zirconium oxide on RGO, and we found that the current induced by the current generated by the PDZR RGO is much higher compared to the ZR RGO composite. Also, it is important for us to know the reaction mechanism so that we could predict how the interference mechanism could occur. So when we studied the reaction mechanism, we found that at minus 0, initially in the first cycle, there is no peak at minus 0.15 volts. The first cycle gives a peak at minus 0.7 volts, which is the reduction of the nitro group to the hydroxylamine group. And subsequently, in the oxidation process at minus 0.3 volts, the hydroxylamine group is converted to the nitroso-phenyl moiety, and then in the ensuring cathodic sweep, this hydroxylamine, that nitroso-phenyl moiety, is reversibly reduced back to the hydroxylamine, and this is the reaction mechanism, and the reactions have been surmised in these two equations for you all. But it is interesting to note that the voltammograms recorded in the absence of the methyl parathion yielded no peaks, stating that there is no electron transfer reaction occurring in the absence of the methyl analyte. Further, it is important to know whether the reaction which is happening if it is a diffusion control process or is a surface driven process. And to study that, we have done the scan rate studies and have plotted the logarithmic plots of peak currents versus the scan rate. And it is known that if the slope of this plot, if it is 0.5 or 0.5, then the corresponding redox process is a diffusion controlled one. And if it equals 1 or if it is more than 0.5 and closer to 1, then it is a surface confined process or a surface defined process. And in this particular experiment, we have found the slope to be around 0.77. And it is evident from the slope that the detection mechanism is clearly a surface-dependent phenomenon. And this surface-dependent phenomenon, this particular experiment highlights the role of zirconia and graphene in the composite material, which is helpful in the detection of the methyl parathion. Further, to ratify our material or our composites as sensitive and selective agents for methyl parathion, we have done differential pulse voltammetric studies. And it is evident from the differential pulse voltammograms which have been plotted here that there is a steady increase in the current with increase in the concentration of the analyte. And the limit of detection for ZrO2 PD RGO composite was found to be 36.8 nanometers. And for ZR RGO composite was found to be 534 nanometers or 0.5 micromolar, sorry, 36.8 nanomolar or 534 nanomolars. And it has also been observed that the ZrO2 PD RGO has a higher linearity over different, very high range of concentrations, but also it has two different linearity ranges, one up to 1.8 micrograms and other from 2 micrograms to 22 micrograms. Whereas in the case of ZR RGO composite, we have found that the linearity range extends only till 5 micrograms per ml. And it is important to understand why this particular. Yes, sir.
You have only 2 more minutes.
Yes, I'm finishing. Thank you. So it is important to understand why this study is very important. First of all, it is important to understand the affinity of zirconia towards phosphate is present in the methyl parathion, and this zirconia interacts, the ZrO bond interacts with the phosphate via the inner sphere mechanism, and also changes in the. Also, it is important to note why. It is important to note why the presence of palladium has made a difference. The presence of palladium or any other noble metal is known to induce a shift in the D band as a result of the changes caused in the surface atomic arrangements. And this shift in the D band leads to decrease in the chemisorption of the hydroxyl ions, which would not go on to poison the zirconium oxide, which would in turn increase the sensitivity of the material. Moreover, these radicals have more affinity towards palladium and not towards zirconium, and hence presence of palladium will lead to a higher sensitivity of the material, and hence overall synergistic effect between zirconia and palladium is important in this material. And we wanted to test whether our material would go on and perform well in the presence of other interfering ions, and we have carried out differential pulse voltammetric studies in the presence of nitrobenzene, paranitrophenol, and nitroaniline in 10 times higher concentration, and we have found that the interference current is not more than 5%. Moreover, to ensure that our material works in the real world application, we have tested out real world samples. That is, we have collected sewage water from our campus, pre-filtered it to remove any particulates, spiked it with the methyl parathion, and have tested it with both the electrochemical method and the tried and tested GCMS, that is gas chromatography and mass spectrometric methods. And we have found that our sample give very good recovery rate and very less range of errors. And here is a comparison of our composite with compared to few of the composites present in the literature, and we have found that our composite performs quite well when compared to other composites in the literature. And in conclusion, we have successfully demonstrated the use of noble metal inclusion in core shell composites as a sacrificial poisoning agent, which has resulted in a 14-fold enhancement in detection limits with 36.8 nanomolar for the composite ZrPD RGO. And the composite was also found to be selective and sensitive towards methyl parathion, as demonstrated by our interfering studies. And in addition, the composite showed very high recovery percentage and high sensitivity and selectivity. I would like to thank Bhagwan Sri Satya Sai Baba, the founder of SSIHL, and also the administration SSIHL Andhra Pradesh, for helping me to carry out the studies. I would like to express my gratitude to Central Research Instruments Facility SSIHL for providing all the instrumental support for this study. I would like to thank authorities at the Japan Advanced Institute of Science and Technology for giving me permission to present this work. And also I would like to thank the organizers of ICONN 2021 for selecting my study as a suitable presentation in this particular conference. Thank you very much.
Okay, thank you very much. Nice talk. So now the time for the discussion. So one question, two questions now I can see on the chat. So good afternoon, sir. How can we confirm the reduced graphene oxide formation from SEM? So did Raman spectrum recorded for the composite? That is the first question.
Yes, sir. Actually, we have recorded Raman spectrum and it is presented here. This is for the graphite oxide, that is after the Hammers method. And here we can see the Raman spectrum for the RGO, that is the formation of the graphene after chemical reduction using hydrazine. And here we have seen that there's a significant increase in the intensity of the D band with respect to G band, which is a confirmation for the formation of chemically reduced graphene or a few layered graphene.
Okay. Next question is, how are the criteria to form the core shell? So can we form core shell of any materials? So first question is, yes, okay, please answer.
Yes, sir. So when we come to the formation of the core shell nanomaterials, there is a lot of, we have first of all, we have to check the surface energies of each material. And we have to ensure, we have to see that whichever material has a higher surface energy over the other will form the core and the other will form the shell. So when we do theoretical studies using the Gibbs free energies and other free energy studies for these different metals and different materials, from there we could decide which will make the core and which will make the shell of the material. And also here we have used a micro-assisted synthesis, which helps in forming the core shell nanomaterials. I hope I am okay with this explanation.
Okay, so any other questions or comments, please? Okay. If not, now time also almost close to finish. Okay, thank you very much for nice talk again.
Thank you, sir. Thank you, everyone. Arigatou gozaimasu.
Okay, so today this session is done. So thank you very much for attending this seminar, and also I appreciate again for all of the speakers. Thank you very much.
Thank you, Professor. Thank you, Professor Minami. Thank you.
Thank you very much.
Kindly fill the Google document for the evaluation sheet. Professor? Professor, you may get the evaluation sheet for the contributory lecture. So,
okay.
Okay, please fill and forward.
Okay.
Thank you, Professor. Thank you. Thank you for.
Okay.
That contributory lecture, the session 3F will end it. The keynote lecture will be started from 12:30. Please be tuned for that talk. Thank you.